My guest today is Vint Cerf, widely regarded as a father of the internet. In the 70s, Vint co-developed the TCP IP protocols that define how data is formatted, transmitted, and received across devices. In essence, his work enabled networks to communicate, thus laying the foundation for the internet as a unified global system. He has received honorary degrees and awards that include the National Medal of Technology, the Turing Award, the Presidential Medal of Freedom, the Marconi Prize, and membership in the National Academy of Engineering. He currently serves as Chief Internet Evangelist at Google. In this episode, Vint and I reflect on the internet path from the ARPANET to the scaling choices that made global connectivity possible. He explains why decentralization was key and how fiber optics and data centers underwrote explosive growth. Vint also addresses today's policy anxieties, including fragmentation, sovereignty walls, and fragile infrastructures, before looking upwards to the interplanetary internet, now linking spacecrafts. Finally, we turn to AI, how LLMs are reshaping learning and software, and why the next leap may be systems that question us back. I hope you enjoy our discussion. Vint, thank you so very much for coming on the podcast. Your work has been incredibly influencing to me, but also to the world, as we will discuss today. So it's a real privilege to talk to you. What I've done is that I divided my questions in two different parts. First, I want to talk about a little tiny thing called the internet and see the role that you played in it and how it scaled and became what it is today. And then I want to talk about the future. I think we can probably learn a lot based on what we've done so far and to look ahead and see where we are heading. So looking at that little thing called the internet, let's start with the beginning. When you developed the TCP IP protocols that, as a reminder, basically allow computers and all devices to communicate over the internet and most private networks, did you envision at the time that they could help what would become the internet scale globally to billions of users, or did scalability come as a surprise?
It did not come as a surprise. This was built into our thinking. First of all, it's important to understand the roots of the internet. It starts with something called the ARPANET, which was an experiment in packet switching that the U.S. Defense Advanced Research Projects Agency undertook in order to link a number of very diverse computers at multiple university campuses who were studying artificial intelligence in the mid to late 1960s. So the ARPANET was intended to accelerate the pace at which artificial intelligence research could progress. So the idea was to have the universities share their software and their computing resources through a network. And the idea of packet switching was at the time very controversial. It wasn't clear whether or not it would serve in the way that it has. So the first network was only 4 nodes, a very small network, but 4 different kinds of computers were involved. And I was a graduate student at the time at UCLA running the Network Measurement Center. Well, I was one of the principal programmers in the Network Measurement Center that was run by Professor Leonard Kleinrock, who, by the way, was a proponent of packet switching and its mathematical analysis. Now, I tell you all that because I want people to understand that this starts in a relatively modest way. There's a book by Katie Hafner called Where Wizards Stay Up Late, The Roots of the Internet, and it's worth reading to get some sense for what that was like, that period of time. Once the ARPANET was running successfully, it was demonstrated publicly in October of 1972 here in Washington, D.C. Bob Kahn, my partner in the internet design, conceived the idea of using computers in command and control and realized he needed to have satellite and mobile radio communication to accomplish that objective because the ARPANET was built out of dedicated telephone circuits connecting the packet switches to each other. You can't do that with mobile vehicles and airplanes and ships at sea. So he came to visit me at Stanford, where I had gone after UCLA, and said, we have a problem. How do we connect these diverse kinds of packet switch networks together? Because they each think they're the only network in the world, and yet we have to find a way to bind them all together. And interestingly enough, down the street at Xerox Palo Alto Research Center, Bob Metcalf was developing the Ethernet. So we had 4 different kinds of packet switch technologies to find a way to interconnect, and TCP and eventually TCP/IP became the vehicle for that. When we were doing this work, when Bob and I were doing the work, we were estimating the scale of the system. And we thought, first of all, maybe there will be 2 networks per country. By the way, we were thinking global. And the reason for that is that the internet was intended to be the basis for the American command and control system, which would have to work everywhere. So we were thinking, okay, so it has to work everywhere in the world. So how many networks will there be in each country? And we said, maybe there should be at least 2 so that there could be some competition. So we were already thinking that this could become a commercialized environment. We weren't motivated by the commercialization, but we were motivated by thinking how to support it. Then we asked ourselves, okay, so don't we have to share this technology with other people, particularly our allies? And of course, yes, because our allies had to be able to interwork with our command and control system. So we said, who are our allies? This is 1973. Then we had a list. And then we said, who were our allies 25 years before? It was a different list. And then we said, who will our allies be 25 years from now? We didn't have a clue. So we said, the only way to be sure that the allies have access to the technology is to share it publicly. So we released it without patents, without any constraint at all. And it's pretty astonishing when you think about it, that the Defense Department is funding this work that eventually becomes the basis for their command and control system. And it's released publicly. And people say today, how did you get away with that? And the answer is, you just heard our rationale. We just did it. Nobody noticed. I suppose if we tried to do that today, maybe it wouldn't be as easy. This is 73 again. We guessed 128 because that's a power of 2, and that's what engineers think in. Well, we were off. It was more like 170 at that point. Today, there's 196 countries. But we just guessed at 128. And we said, okay, so 2 per country, that's 256 networks. We were thinking national scale networks here, not little Ethernets. And so that's 8 bits would be needed to represent a network number. So each network had its own number. And then we said, okay, how many computers will there be per network? Now, remember, this is 1973. Computers are multi-million-dollar things. And we said, why don't we just allow for 2 to the 24th, another 24 bits. So we had a 32-bit address, 8 bits of number of network, and 24 bits of a computer on the network. The internet gets turned on formally in 1983. It officially launched operationally. By 1992, we suddenly realized that networks are proliferating, especially local area networks, Ethernets and other analogs of that. And we were running out of address space because it wasn't being allocated in the most dense way possible. So the Internet Engineering Task Force, which is a place that established standards, realized that it needed more addresses than could be made available with the 32-bit address. That was called IP version 4. So IP version 6 was developed over a 4-year period and then standardized in 1996. And at that point, I thought everyone would just drop IP version 4 and implement IP version 6 because it was still a fairly small community. However, I hadn't taken into account that we were in the middle of what was called the dot boom, which was the result of the introduction of the World Wide Web by Tim Berners-Lee. He did that work and announced it in December of 91. Not too many people noticed, but 2 guys at the National Center for Supercomputer Applications, Mark Andreessen and Eric Bina, developed a graphical user interface browser called Mosaic. And they released that publicly because NCSA is a not-for-profit organization supported by the U.S. government. And everybody downloaded this beautiful browser. And at this point, the dot boom is on. Netscape Communications gets started using people who had developed Mosaic to develop the Netscape Navigator. They went public in 1996. And so just as we're standardizing the IP version 628-bit address space, the dot boom is distracting everyone from anything else. So IPv6, which has 3.4 times 10 to the 38th addresses, which is enough to last until after I'm dead and then it's somebody else's problem, is only about 35 or 40% adopted and implemented across the internet. More than half of all the traffic in the internet is carried on IPv6, and that's because so much of the traffic is video. We tried to anticipate scaling by introducing V6, and that's still slowly getting implemented. One particularly significant moment occurs during the mid-1980s. After ARPA had built the ARPANET, the Department of Energy, NASA, and the National Science Foundation built backbone internets of their own and then interconnected them. The NSF system also interconnected about 12 or 13 regional internets to connect universities to supercomputer centers that had been funded by NSF and DOE. That forced us to develop a routing protocol, which today we call the Border Gateway Protocol, in order to scale up the network. And so there were conscious points in the internet's evolution where scaling was the key issue, and steps were taken in order to increase its capacity. The other thing that scaled very rapidly starting in the 1980s is optical fiber technology, which today carries 400 to 800 gigabits per second per channel, per optical channel in a single fiber. Single fibers can carry multiple wavelengths, and so the capacity is just absolutely mind-boggling. And of course, that's why we can do what we're doing this very moment, which is recording audio and video in real time. To say nothing of having literally some 6 billion users all interacting with various websites scattered all over the world. So that's another place where scaling turned out to be super important. Otherwise, we couldn't handle what we're doing today. So optical fiber technology, free space laser technology. How about computing? With millions and now billions of people using the internet, they're using computers, their own plus the cloud-based systems. And so computing needed to grow in capacity as well. And as you well know, there was Moore's law, which was an observation by Moore that it looked like the number of transistors on a chip was doubling every 18 months. And that increased total capacity of each chip. That eventually Moore's law stopped because you couldn't make transistors any smaller than a certain size. But what has happened is that, and the clock speeds were also going up very quickly. Eventually, you couldn't run the clock any faster or the chip would melt because of the amount of energy it was using. So the next step was to have multiple computers on a single chip. It's called multiple cores. Then the next thing that happens is that we find there are other ways of doing computation than the conventional CPU, central processing unit. We end up with graphical processing units that do one thing really fast, and that's draw little triangles. And they do that by doing a kind of matrix multiplication. Then we get artificial intelligence and multi-layer neural networks, and we discover that they too would benefit from yet another kind of computing, which at Google we call tensor processing units, which again do a very sophisticated matrix multiplication at very high speeds. The consequence of that is the scaling up of computing capacity. And the next step after that, of course, is quantum computing, which doesn't work for every possible application, but for certain kinds of optimization applications and also for certain kinds of code cracking, it's a perfect tool. Well, IBM does have a product, and Google is running chipsets for quantum computing that are up in the 200 qubit size, but you need hundreds of thousands, if not millions of qubits to do something serious. So we're still on the path of development there. But again, that's another scaling effect, because quantum computers will compress the time it takes to do certain kinds of calculations. It would take a really long time with conventional machines. So here we are. We've scaled up by a factor of something like 1 to 10 million over a course of 50 years. And it's quite remarkable that a particular architecture is capable of expanding to that extent. The design had the capacity to do that.
So that's an incredible overview of the design and the technical part. From what I understand, you had at least a vision for the fact that this would be possible and that this could scale. Now, what's very interesting is that you not only helped the design of the protocol, but you later became active in promoting internet standards. And you've done that through organizations like the Internet Architecture Board, the Internet Engineering Task Force that you've mentioned, ICANN, others. Looking back, are there limits to scaling that those organizations have helped resolved?
Clearly, the Internet Engineering Task Force and the Internet Architecture Board have had and continue to have an enormous influence on the basic standards that allow the Internet to function. Here's the thing. When Bob and I were doing this design, we had the experience of the ARPANET behind us. And one of the features of the ARPANET was a layering of protocols. The lowest levels were all about sending bits on wires or eventually on fibers. And then the next level up organizes these bits into a frame. And the next level up organizes the frames into packets. And packets have addresses in them, the to address and a from address and some content. Then the next level up is managing the packets as a flow to make sure every packet gets there in the right order. Although there were other applications where you didn't care if all the packets got there, but you wanted to get them there as quickly as possible. For example, radar. You don't care where the missile was. You want to know where the missile is. So if you lose one of the radar tracks, you don't care about that. Packets, voice and packet video is very similar. If you lose a packet, don't retransmit it because it increases the latency of the discussion. And that's very disconcerting. I guess the point I want to make here is that these institutions were absolutely essential in the technical evolution of the internet, and they are still that true today. There's another organization called the World Wide Web Consortium, which was created after the World Wide Web was introduced, and it too has become a vital part of web evolution. The domain names and the IP address spaces were managed by one guy, a guy named John Postel at USC Information Sciences Institute in Los Angeles under government contract, under DARPA contract. Eventually, the contracts moved from one agency to another, to the National Science Foundation, and then to the National Telecommunications and Information Agency. But these were government-funded activities, and at some point, people were saying, this is so fully immersed in the commercial world. The first commercial internet service comes in 1989. And at some point, the government's saying, why should the government pay for this? This ought to be self-supporting out of the commercial world. And so the Internet Corporation for Assigned Names and Numbers was started in 1998 to perform this function, and eventually became, I would say, disconnected from the U.S. government in 2016 as a completely independent body. Around 1992, I helped to create the Internet Society. And the reason I had to do that is that the National Science Foundation eventually said, we've been paying for the Internet Engineering Task Force support, the Secretariat, for some time now. We're spending research dollars on something which is clearly increasingly of commercial interest. So you should become self-supporting. And I remember thinking, they told me this in 1990 or so. And I remember thinking, oh, I guess I better create an institution that can ask for money, a nonprofit institution to ask for money to support the Secretariat. So Bob Kahn helped to create the Internet Society. We spun it out from his company, the Corporation for National Research Initiatives, and I became the first president. And that organization has since blossomed into a major operation. It is responsible for running the .org top-level domain, which produces something like $70 or $80 million a year in income, which can be used to support all the Internet Society activities. So these institutions have become central, frankly, to the Internet's stability and long-term operation. Lots and lots of networks need to be interconnected. Instead, they go to an Internet exchange point, so they all run their optical fiber to one place, and then they cross-connect. And so these Internet exchange points have become very important to the resilience and connectivity of the Internet. Again, another set of institutions that are very important, along with the domain name registrars and the domain name registries.
So it seems that you have a design that was from the get-go put in a way so that the internet could scale. And then you have the governance part of it, with all of those organizations played a very important role. Moving closer to today, how did the decentralized nature of the internet architecture contribute or maybe complicated its scaling? Could the internet have scaled in the same way with a more central architecture?
I don't think so. In fact, let me go back to layering for just one moment, because I remember I should have told you one other thing about scaling. The layered architecture had functionality in different layers, becomes more and more sophisticated as you go up towards the top, or more application oriented. But the thing is, we designed it so that if you didn't like the protocols at a given layer, you could add one. And so when optical fiber came along, we just added optical fiber to the list of other carriers of bits. So the internet protocol layer was perfectly happy riding on anything that would carry a bit. When Tim Berners-Lee came along, he looks at TCP/IP. He says, well, that's a ubiquitous thing that allows every computer to talk to every other computer. So why don't I just plop down the hypertext transport protocol on top of TCP/IP, and that means it'll go everywhere. And that's exactly what he did. We designed it so that adding a new layer was okay. Adding another protocol within a layer is okay. There are hundreds of protocols that are part of the internet environment. That's another kind of scaling, which was deliberately accommodated because we knew we didn't know everything about what people would want to do with this capability of computer-to-computer interaction. So now let me come back to the question that you were asking about decentralization and centralization. In some ways, of course, the thing starts with a very central control. Bob Kahn and I essentially ran the internet project for quite a while. I was at Stanford from 73 to 76, and then they asked me to come to Washington to run the program for the Defense Department from 76 to 1982. And at the end of 82, we turned the internet on operationally. So there was central control there, and we steered this, but boy, did we rely on smart people. We had lots of help from really smart people, some of whom had worked on the ARPANET project and others who had come in later on. But the system was deliberately designed for multiple networks to be interconnected. We had no restrictions on which technologies were being used. They just all had to follow the same TCP/IP architecture. But we didn't care whether it was bits on a wire or on an optical fiber or over the air by radio or on a laser link. So there was huge flexibility. And we also assumed that there would be different business models, that networks would be created by the governments, by the private sector, for profit or not for profit. And we didn't care. We just said, however you build this thing, just make sure you follow the same TCP/IP protocol rules and you'll be able to interwork. So we assumed that the only way it would scale up would be if multiple parties discovered reasons to invest in a network and to operate it and to offer services under some terms and conditions. So that was another part of the scaling. Networks have come and gone. The original networks of the ARPANET are all gone now. ARPANET, packet radio net, packet satellite net were all core to the original internet, and they're all gone now. And yet we have tens of thousands of networks all around the world that are part of this fabric. So decentralization was essential not only to allow for local decision-making, local operations, and allow multiple networks to interconnect, but I think also for investment. Who would want to pay for a network? Somebody who had a business model that would make it just sustainable.
Now, are there moments, looking back from today's perspective, you think the internet's architecture was very close to tipping toward more centralization and thus, if I understand, stop scaling?
Well, of course, we were quite worried when IP version 4 was starting to run out of address space and we switched over to V6. As it happened, somebody invented another idea called network address translation and private address space. Network address translation meant that a routable IP address one address could be used to communicate with a whole bunch of other devices that were on the other side of that routable IP address using local network addresses. that we didn't run out of IP version 4 as fast as we thought we were going to run out of it because of its network address translation, which is why we don't have as much V6 as I would have liked. But I think we're starting to reach a tipping point where V6 is becoming natural. Most of the mobiles in the world use V6 and not V4, for example, and there are lots of those. One thing I will say, though, is some people complain about this, is that some of the parties in the internet environment, whether they're application providers like we are at Google, or they are underlying network providers, have gotten very big. And the question is that a bad thing? And I think the answer is that it's almost inescapable because of economy of scale. If you just think for a minute about what it takes to build, for example, a global optical fiber network or a data center, usually it's less expensive to build a large data center than a whole bunch of little ones. And the reason for that is that the number of people required to manage a data center does not scale linearly. We use lots and lots of automated methods in order to run the data center. So a big data center requires a smaller number of people than would otherwise be imagined. And on top of that, it's more efficient to build a significant number of large data centers. However, you also distribute them for at least two reasons. One is resilience. You don't want a common failure to knock all your data centers down because all the power is gone. Puerto Rico has experienced massive power failures. So we locate our data centers, as do others, in different locations around the world. The other advantage to doing that is that you reduce the latency for the users who are interacting with the data centers. One thing you can see with regard to scaling is that first we have really big data centers and relatively, let's say, simple-minded access devices like teletypes and terminals and things like that. Then you start building computers that are local. So you have desktops, you have laptops, you have pads and things like that, and now mobiles, and they interact with each other. And now we're getting edge computing, which is computers that are between you and your mobile or your laptop and the data centers. There's more computing available closer to you. Content distribution networks are a lot like that. That's how we distribute video, by making a copy at a data center or at a head end of an optical fiber system. And then we distribute from that location. So we don't have to transmit the data all the way across the Atlantic or the Pacific multiple times. We just do it once, and then it's locally served from the content distribution network. All of these are features for allowing scaling up of services.
Yeah, so you've mentioned the economies of scale, which makes me want to ask you one last question for part one of our conversation about the parallels, if any, between biological systems and the internet evolution. Because, of course, in a physical world, you tend to have more decreasing returns than online. But maybe Darwin can also teach us about similarities when it comes to survival. So, any thoughts on the subject?
I'm an amateur student of biology. I'm very interested in multicellular systems. And you notice that in a multicellular system, human body, of course, is not only multicellular, but the cells are organized in organs and they collaborate with each other. There's a kind of a funny layered architecture there. Lots of cells at the bottom layer, but then the cells are differentiated and they form different kinds of organs, and the organs interact with each other. And then there's the neural network up here, which has a lot to do with the functioning of the other organs, like the autonomic system. So the question is there any analogy that we can draw? And I guess I don't honestly think that the analogies are very strict at this point. A strong indication that biology will tell us how to build more efficient data centers. I will say, however, that there is something interesting going on in the large language model multi-layer neural network space, where these systems appear to perform functions that humans and other intelligent species are able to perform, but there's no indication that we're doing it the same way that our brains do. So I'm still unsure how much we will learn from biological systems, except for the fact that we know that communication among the various components is very important. We have a very complex internal communication system in our bodies. of varying kinds. Sometimes it's electrochemical, which is along the neural structure, but sometimes it's just small molecules that are used as signaling both inside of cells. There's signaling going on inside of a cell, and there's signaling going on between cells. And at least one person at the University of California, San Diego, sent me a note saying, I found an internet inside the cells. And I'm thinking, what are you talking about? And she said, we can see that there are microtubules inside each cell. And we can see proteins that crawl along the microtubules, and they're carrying little molecules that have labels on them that say where they're supposed to go, which sounds an awful lot like a packet. And so there are complex processes for signaling using small molecules inside of cells that kind of look a little bit like packet switching.
And on top of that, you may have complex relationships between organic and digital objects, which is a perfect segue to part 2 of our conversation, talking about the future and AI. But before we talk AI, one more question about the internet and its future. Is there a risk that the internet will fracture into separate internets? It seems to me that the global push for self-sovereignty is moving us in this direction, but is the risk real, or do you think this will actually go away?
No, there are many different places where the internet can fragment. It could be people trying to build barriers between the national internet and the rest of the world. China is a good example of that with all kinds of filters. Others are trying to do similar kinds of things. What they are doing, however, is essentially interfering with their own ability to take advantage of the internet for economic development and for trade. And so none of this works unless you have relatively free flow of data from one part of the world to another. The internet was designed without consideration of crossing international boundaries. The packets don't know when they're crossing those boundaries. And that was important because it was supposed to work all around the world for the Defense Department's command and control system. But there is a risk that there will be fragmentation. And at various levels, there can be fragmentation up at the domain name level because the system is prevented from resolving a domain name. So you can't get to the IP address to get to the service side. I think that policymakers need to understand a little bit better that it's the connectivity of the internet that has given it such value. And that putting barriers in between pieces of internet is a good way of killing the golden goose. But I have to relay that lesson repeatedly in places like the Internet Governance Forum and other parts of the United Nations and to policymakers around the world, which is why the chief internet evangelist at Google does a lot of traveling to meet with people and to try to convince them that they need to take a more egalitarian view of the value of internet connectivity.
Please tell me more about that.
Okay, so back in 1998, the U.S. successfully landed a Pathfinder rover, the Sojourner rover, on Mars. And we had landed successfully 20 years before that in 1976. The two Viking 1 and 2 landers arrived successfully. Not long thereafter, we launched the Voyager 1 and 2, which are now some 13 billion miles away in literally interstellar space. And then for 20 years, nothing worked. We tried to go to Mars and we burned up in the atmosphere, or we crashed on the planet, or we missed the planet entirely. And then, so this 1997 lander was a big, exciting event. And I got so excited about it, I got together with the Jet Propulsion Lab people who were handling communications for that system. And we started asking ourselves in the spring of 98, what should we be doing now, that is to say in 1998, that we're going to need 25 years from now? And we decided we should design and build an interplanetary extension of the internet to support manned and robotic space exploration. So we began that process way back in 1998. Here we are, it's 2025. We have a new suite of protocols that we call the Bundle Protocol Suite that is designed to service communications in deep space. Now, here we have a problem. The speed of light is limited. And so the latencies for communication from one place to another are very big. Talking to the Voyagers takes 22 and a half hours for the signal to propagate from Earth to the Voyager, and of course another 22 and a half to come back. There are other cases going to the outer planets, even to Mars, for example. When we're closest together, it still takes 3.5 minutes for a signal to go from Earth to Mars and another 3.5 to come back. And when we're farthest apart in our orbits, it's 20 minutes one way and 40 minutes round trip. The TCP/IP protocols were not designed for that. And so we developed what we call a delay and disruption tolerant networking protocols, DTN for short. And the manifestation of that is called the Bundle Protocol Suite. That work has been implemented now over a period of a couple of decades. We've been on the International Space Station operating since 2016. We've done communications to the moon. We've done communications with other spacecraft that are farther away. And we're part of the Artemis return to the moon missions that the U.S., ESA, NASA, and JAXA are involved in. So it's a very exciting moment in time in 2025, looking forward to deep space exploration and support for communications using an interplanetary internet.
So when it comes to the future, we talked about fragmentation of the internet on Earth, complemented by potential expansion to the outer space. Now, of course, another big change is AI. And it seems that the more it goes, the more AI systems are interacting with each other through APIs, autonomous agents, and so on. Are we about to witness a scaling process that is similar to the internet? Or do you think it will be slower, faster? And I guess we can come back to the power laws, the Moore's laws, and the others that we discuss as a way to predict where we are heading.
I'm not expert in the AI implementations, even though Google has been far in advance of many others for quite some time. I will say, though, that all of the observation from the last, let's say, 24 months or so is that this pace at which developments are happening is accelerating. The scale of the systems is just mind-bogglingly big. The amount of information that's ingested into the system and modeled by the multi-layer neural networks is also just quite astonishing. The consequence is that these systems are showing capabilities that I certainly didn't anticipate. At Google, for example, we're using some of our large language models to assist our programmers to speed up their ability to write software on which everything, of course, works in this space. Our CEO was quoted as saying that somewhere between 25 and 30% of the software that we presently develop is being developed through the support of artificial intelligence. Of course, then it gets scrutinized very carefully before we actually put it into operation because these systems are not always 100% reliable. So I'm seeing an accelerating pace here. This probably will be another one of those S-curve things where we're on the steep part of the S-curve right now. And maybe we will get to a point where there aren't more gains to be made with the current methods of AI. But you never want to second guess these things. Every S-curve that I've ever experienced has had the roots of another one hiding in it, and it takes off when the first one runs out of gas. So there may very well be some unusual developments, partly created through the means of these current large language models that we just don't foresee. We're seeing some pretty remarkable results, including discovery of designs that we thought were not possible. A kind of example of this, which will sound overly academic to the listeners, was figuring out that when you're doing a matrix multiply, which is a core element of large language models and neural networks, that somebody 56 years ago said that in order to do a 4x4 or a 2x2 multiply, you needed exactly 49 multiplies, and you couldn't do it any less than that. And we set one of what was called alpha evolve system to work on the problem, and it found a way to do it in 48 multiplies instead of 49. Now, that doesn't sound like much, but when you're doing billions and billions of multiplications per minute, saving one actually is a big deal. And so these tools are helping us discover solutions in spaces that we could not explore ourselves because it's too vast.
And indeed, you've mentioned the technical advances and the role that Google has been playing. Google is the company, or at least some researchers behind the transformer technology. I also like to use the alpha chip example where you have developed this new graph neural network to learn the relationships between the chip components and the design of those chips and how to run systems. So you see the interplay between hardware and software as we explored today. Now, moving away from those technical discussions, what role should or are public institutions such as the one that you once worked with play in shaping AI? Is there something that is very obvious to you already in 2025, or is it too soon to say?
I would say that as we look at our world of 2025, we are increasingly dependent on software constructs to do things for us. Of course, those software constructs have to run on top of a physical infrastructure. And the more that we depend on it, the more important it is that the infrastructure be reliable and sustainable and accessible. But this dependence, I think, has a price. I would suggest to your listeners to imagine what the day would be like if your mobile wasn't working. And my guess is that it would not be a good day because there are so many things that people with mobiles depend on it doing for you or with you in the course of the day. You're standing on the corner and you're waiting for a taxi and you think it would be easier if I just called Lyft or Uber, but your mobile isn't working. So now you're stuck. And I'm sure there are literally a bazillion other applications that people rely on a daily basis in order to do their work or find entertainment or make arrangements for travel, conducting business, buying things. All of those things have been made easy by mobiles and applications of the internet and the World Wide Web. But it rests on this infrastructure, which has to be maintained. It requires power, it requires cooling capability, it requires maintenance. Believe me, the internet doesn't run by itself, nor do the data centers. People are involved on a regular hour-by-hour basis, 24 hours a day, maintaining these systems, which break from time to time. Pieces stop working, and you have to fix that or replace them. People have to do that. And this entire infrastructure, which is wonderful when it works, also has a downside because when it doesn't work, there are all kinds of consequences. This is true of all infrastructure. We don't think about the infrastructure because we're very reliant on it. We don't think about it. When the power goes out, suddenly we realize, oh, we were really dependent on power. Now I don't have it. What do I do now? Same with streets and roads. When the roads get blocked, suddenly you can't go where you wanted to go. And you think, gee, I didn't realize how dependent I was on the damn road system, except now I can't go anywhere. And you can come up with examples of things that we think of as infrastructure that we don't think about, except for the people who maintain it. And they think about it all the time, but we don't. And that's the nature of infrastructure.
So I just returned from a trip in Asia, and there many of the LLMs that I like to use are not available, which made me realize just 1 hour after landing how dependent I am already on those LLMs. But if I understand correctly, you would say the role of those public institutions could be to make those systems more robust and less fragile in a sense.
In fact, one of the organizations that I used to chair is the Marconi Society, which has been around since 1974. It gives an annual award called the Marconi Fellowship. It was started by Marconi's youngest daughter, Gioia Braga, way back in 1974. We recently, at the Marconi Society, started several initiatives, one of which is all about internet resilience. And we're looking at that question, how resilient is the internet? How could we make it more resilient? What steps could we take that would make it more reliable? The deep dependence on electricity is interesting. And there's even a kind of a recursion here because the power systems are using internet technology more and more for their management. And so they are now codependent in many ways. And so the codependence creates a certain amount of potential fragility. And we need to understand that and make sure that we've accounted for that in the architecture.
Yeah, exactly like the making of chips for AI training, which can be used by AI. Let me ask one final question. So if the internet began as a tool or infrastructure for interconnecting computers and is now becoming a layer for interconnecting intelligences, whether on Earth or in the outer space, where does the story go next? Is there any very bold prediction that maybe you never dared to say before that you could make right now?
Well, predictions, I think, are not my strong suit. I'm the guy that thought 32 bits was enough for the address space. Any other more deep prediction?
Just between us, not recorded, of course. So please go ahead.
I think that my expectation now, having had some exposure to the capability of large language models, about which I was rather skeptical. I was experiencing the kind of hallucinations that the specialists talk about, and that was amusing, and you made fun of them. But in the recent past, the last few months, I have been experimenting with some of the large language models that we operate at Google, particularly the Gemini class. And I must say that there is an extraordinary thing happening in those systems. It's a different way of getting access to and experiencing information. For years, of course, writing things down in scrolls and books was how we passed on knowledge to the future and how we passed knowledge to other people in the present. Now, the interaction with these large language models is a different way of learning about and understanding information than we have used in the past. We had very linear methods. Reading a book is a linear method of gathering information. The ability to interact with a large language model gives you extraordinary flexibility, and it also is a way of experiencing an extraordinarily broad range of context and content. So your exploration is unlimited in some sense. When you ask a question, you get back a synthesis of an enormous amount of information. The recall is astonishing, and it does things that no human being could do, certainly not in a finite amount of time. Translating languages is something we use these models for and have done for quite a while. They can do 200 languages, 40,000 different ways of doing translations. The quality varies depending on the source materials that's available to do the training. So I am convinced that we are entering into a period where we will experience information and have a facility for applying it in ways that we never had before because of the interactive character of these systems. One thing I am waiting for and expecting is that we will move from the ask a question, get an answer kind of exchange to the systems themselves posing questions. Now, this would be quite an extraordinary transformation because they become tutors. If you think about the tutorial practice at Oxford, what do you hear people say? They say, I am reading X for some value of X, some topic, and I have a tutor. And what does the tutor do? The tutor asks you questions about what you have read. So I am waiting for the large language models to start asking questions and becoming tutors, taking us through, guiding us through our learning, and then perhaps doing things for us, if not to us. So the agentic AI agents are the next obvious thing coming. And watching multiple agents interacting with each other is going to be fascinating. I'm actually attending a PhD defense this afternoon by one of our Google colleagues, which deals exactly with multi-agent interaction. So this is clearly coming. And of course, humans will be part of that loop as well.
With one of the last guests on the podcast, James Evans, we actually talked about how we could potentially, as academic, explore conferences run and simulated by AI agents and take and derive something from it. And as a teacher, of course, I'm trying to build fine-tuned LLMs that I could give my students access to so that they could interact with the content of a course and have a voice that they could trust in the space. But it's not easy so far to design. If I may ask one very bonus final question, looking back at your career and what you are doing nowadays, what is an important question that you get rarely asked and that you wish will actually be asked a bit more?
Oh, then the most common one is, did you have any idea the internet was going to get this big? That's question number 101. Oh, I don't know. I guess it would be interesting for someone to ask a bit more about what you have done. What are my expectations as this thing evolves? My expectations are quite limited by my understanding of the technology of today. So I would like help, actually, more rather than me answering a question or be asked a question. I would like to be able to ask the questions myself of people who are themselves looking towards the future and are schooled in today's technology as opposed to yesterday's technology, and probably can answer the question better than I can.
Yeah, I think, if I may say, it's very inspiring to hear you say that because of your expertise and knowledge and everything that you can bring on the table. I wish I can retain the same attitude in my career. So on that very good note, thank you so very much for a very deep and interesting and stimulating conversation. I hope to see you in person one day, whether in the US or the EU or elsewhere. And to everyone out there, take care of yourself, and if you can, someone else too. Bye-bye.
Thanks so much. Bye for now.